mathematical physics, so I'll have a lot of physics in the talk. So if there are any questions or anything you don't understand, please interrupt me. So I'm going to talk about how to use higher categories to construct something a physicist would see as observables for the Turaev-Viro model. And all the contents of my talk, that's worked together with John Barrett. It's not yet on the archive, but I hope it will be soon. Okay. So the motivation. So what is our motivation for considering this is the role of the Turaev-Viro model or the Turaev-Viro invariant. So that is important in mathematical physics. It comes up in several contexts. So one is state sum models of quantum gravity in 3 dimensions. But there are also branches of other mathematical physics topics, for example, topological quantum field theory and conformal field theory and higher gauge theory. And finally, it's also interesting from the mathematics point of view because it brings together essentially topology and algebra. So more precisely, topology and the representation theory of certain Hopf algebras. So for this reason, this is a model that mathematical physicists consider important. And what it does, it takes a closed triangulated three-manifold with a piecewise linear manifold and associates with the complex number. And this complex number is invariant under change of triangulation or under piecewise linear homomorphism. And if one takes the triangulated manifold with the boundary, it works in a similar way. In this case, the Turaev-Viro invariant associates to each boundary component a finite dimensional Hilbert space and gives a map between these Hilbert spaces associated with the boundary components. And this has a physical interpretation that comes from topological quantum field theory or quantum gravity. So there one associates, one says that each of these elements of the Hilbert spaces is a physical state, and this map between the Hilbert spaces gives so-called transition amplitudes between geometries. So one thinks that the elements of a Hilbert space characterize something like a quantized geometry, and the Turaev-Viro invariant then tells us the probability essentially to go from one geometry to the next. So that's sort of the interpretation. So there are a lot of things that are vague there, and there's one thing especially that is difficult or that is lacking. And the problem is to obtain something that one would call observables, or that deserve the name observables. So in physics, one would not be happy to simply have a Hilbert space. A quantum theory just consists of Hilbert spaces alone and of transition amplitudes, but one would want to have observables that tell us what could be the things that can be measured and what could be the possible outcomes of measurements. And how to define observables for such a model is not clear at all. So there are some results that are for specific cases, some results or ideas in the context of quantum gravity, but there's no general way of defining observables or no general result or formalism. And especially it's also not clear what would be the underlying mathematical structure that would allow one to define an observable. So what is it supposed to be in mathematical terms? So this is the question essentially that motivated our work, and I try to sketch some answer to this in the talk. And the talk will be structured as follows. So first I'll give a brief summary of generalized Turaev-Viro models or Turaev-Viro invariants. Then I'll talk about the central idea of the work, namely to get observables by using higher categories. Then I'll make this a bit more precise and say what higher category I'm going to use and how these observables can be built. Then I'll define the model and say how to evaluate it. And in the last part of the talk, I comment on the relation of this model with Barrett-Turaev invariants, which are another set of observables for the same theory, but with a different quantization approach. And in the end, I'll summarize some of the results and discuss what they can be used for. Okay, so I'll start by talking about the generalized Turaev-Viro models. So the Turaev-Viro invariant or Turaev-Viro model was first induced by Turaev and Viro, and they constructed invariants of piecewise linear manifolds by using the representation theory of a Q-deformed UQ of SU2 or another Q-deformed universal enveloping algebra at the root of unity. then later this was revisited by Barrett and Meusburger, and they gave a generalization that is formulated in categories, more specifically in terms of non-degenerate, semi-simple, spherical categories. Okay? So I'll briefly describe what this is. So a non-degenerate, semi-simple spherical category is essentially a pivotal fusion category that is non-degenerate and in which the left trace is equal to the right trace. So that means the following things. So first, this is supposed to be a monoidal category with strict rules. So one is a tensor product, a tensor unit, and in the following I'll use graphical notations and diagrams for everything. So the objects of the monoidal category are depicted by oriented arrows. The morphisms are vertices between different arrows. The composition of morphisms is putting the vertices below each other, so everything is read from top to bottom. And the tensor product is putting these arrows denoting the objects next to each other. So that's just the standard notation. But then it's not just a monoidal category, but it's supposed to have duals. It means one has a contravariant strict tensor factor, such which are denoted by a star, such that star is equal to the identity. And the diagrams for this, so the star means simply inverting the direction of the arrow. So the dual of an object is the arrow pointing in the opposite direction, and the dual of the morphism, one also just inverts the corresponding diagram. So then in addition to that, it's supposed to be pivotal. It means that for each object in this category, one has a morphism that goes from the unit for the tensor product to the tensor product of the object and its dual. That's called the co-evaluation. And that is denoted by an oriented arc, like I've shown here. And it's not just such a collection of morphisms, but morphisms have to satisfy certain conditions. First, they should be compatible with the morphisms in the monoidal category. That means I can slide a morphism past this arc, and then I get a dual. Then they should be compatible with the tensor product. That means that this picture I've drawn here has a clear interpretation. One can interpret it in two ways, as the co-evaluation of X tensor Z. But one can also interpret it as a certain combination of the co-evaluation for Z and for X. And these are supposed to be equal. And the last identity is that if I compose the co-evaluation with its dual, which is the evaluation, I get the identity. Okay. So in addition to that, it's supposed to be spherical. That means that the left and the right trace agree. So using the structure of the pivotal category, I can construct the left trace that I've given here and the right trace for each endomorphism alpha of a certain object. And the condition for spherical is now that the two are the same. And then finally, it's supposed to be a non-degenerate fusion category. So the endomorphisms of the tensor unit are supposed to be isomorphic to C. Each of the morphism spaces should be a finite dimensional vector space over C, and the tensor product and the dual are supposed to be C bilinear or linear.
Excuse me? Did I miss that? Is the tensor product symmetrical? Or do you have a breaking at the moment?
There's no condition on if the tensor product is symmetrical.
So how do you define the evaluation in the opposite direction and the co-evaluation?
So if you're given the co-evaluation, so you have this, then you can define, first you can define this. This is simply the co-evaluation for X star. And then you take the dual of the, so that's the evaluation. And then you take the dual of this. So that's simply the dual, so this is a morphism and this is the dual morphism. Maybe I've switched these two pictures, but you don't need the symmetric. Okay. And then using the trace, one can define a pairing between the space of morphisms from one object to another one and the opposite way. And this pairing is supposed to be non-degenerate. And finally, it's supposed to be semi-simple. That means that there exists a set of non-trivial simple objects for which the endomorphism space is isomorphic to C. And such that the natural map that I've given here is an isomorphism of vector spaces. And finally, okay, and the picture for this I've drawn here, so that's That's like a whatever takes the sum over the things in the middle. And the last condition is that it's finite, so the set of isomorphism equivalence classes of simple objects is supposed to be finite. Okay. So this is simply the category formulation of the representation theory of Q-deformed universal enveloping algebras at the root of unity. And that is kind of the most general structure that can be used as a building block for building the Turaev-Viro invariant, or generalized Turaev-Viro invariant. Okay, so how does this work? So the Turaev-Viro invariant constructs invariants of a piecewise linear three-manifolds from these non-degenerate semi-simple spherical categories. So the ingredients are a triangulated three-manifold and a non-degenerate finite semi-simple spherical category. Then one labels the edges and faces and vertices and tetrahedra in the triangulation with data from the category. So to each oriented edge, one associates a simple object, and if the edge is reversed, one associates the dual object to it. And for each oriented triangle, one associates a morphism between the simple objects at the boundary of this triangle. So the corresponding picture is here, so one has a triangle, and the morphism is just the dual of this triangle. I mean the dual graph of the triangle picture. And if one reverses the orientation of the triangle, one gets simply the dual morphism. And for each tetrahedron, one can then define a tetrahedron amplitude. So one has a tetrahedron with objects at the edges and with morphisms at the faces. And one associates with the so-called 6J symbol. So that's a morphism from the tensor product of the morphism spaces associated with the faces to C. And the corresponding picture is this. So one sees it's obtained by composing these morphisms in a certain way, taking into account the orientation of the tetrahedron and of the triangles. Okay. And using the tetrahedron amplitude, one can then construct an amplitude of a labeled triangulation that is simply by taking the product of the tetrahedron amplitude for all the tetrahedra in the triangulation, always taking into account the orientation. Okay, and from this one can construct the Turaev-Viro invariant, the formula I've given there. So first one takes the amplitude for the labeled triangulation. Then one multiplies it with the Q dimensions of the objects of all associated with all the edges. So that's simply the trace of the identity morphism for the object. Then one sums over all the assignments of simple objects to edges. And in the end one rescales it with a certain factor, k. And the minus v here, v is simply the number of vertices in there. So that's the Turaev-Viro invariant in the categorical formulation. And it defines for each closed triangulated three-manifold a complex number. And this number is invariant. What does this mean? So if I have two triangulations, I can relate them by a finite sequence of Pachner moves. So these are the moves I've given here. So one is simply subdividing a tetrahedron into 4, and its inverse, and the other one is subdividing two joint tetrahedra by adding a line in the middle. They are also called bistellar moves. And the Turaev-Viro invariant is invariant under the Pachner moves, and it is essentially a consequence of two identities. So for the subdivision moves, I've given the identity here. This is sort of called orthogonality of 6J symbols, or it generalizes the orthogonality relations for the 6J symbols one knows from the representations. And the second one for the 2-3 move is the so-called generalized Biedenheim-Elliott relation. And the fact that these relations hold is precisely the consequence of the properties of the non-degenerate semi-simple finite spherical category. So the category is built in such a way that one can define and get these relations. Okay. And for manifolds with boundary, this works in a similar way. Only the morphisms and the objects at the boundary, there's no some information over the assignments at the boundary. And then one gets a similar invariant that depends only on the data of the boundary, not on the internal data. Okay, so this was a brief summary of the Turaev-Viro invariant. Now I'm going to talk about the issue of getting observables. So the Turaev-Viro invariant, as I've mentioned briefly, has a physical interpretation from topological quantum field theory or quantum gravity. So in particular, one can understand the Turaev-Viro model as a quantum theory of Euclidean 3D gravity with a positive cosmological constant. And in this interpretation, one interprets this Turaev-Viro invariant C of M as a state sum, similar to models from statistical physics or some discrete path integral formalism. And the data at the boundary is supposed to give the physical states, and the Turaev-Viro invariant then defines an inner product or transition amplitudes between these spaces. So for instance, if one has a manifold where the boundary is a disjoint union of two components, then one has for each component one has a finite dimensional Hilbert space that is constructed from the morphism spaces associated to the triangles at the boundary. And then the Turaev-Viro invariant defines a map that goes from the tensor product of these spaces, one has to be taken as the dual, to the complex numbers. And it defines something like an inner product, and this inner product has the interpretation of the transition amplitude from one state to the other one. But the question of this is now how to introduce the observables into this description. And naively one would say, if one takes the analogy with statistical physics or discrete path integral formalisms, one would say, okay, so an observable is some function that depends on the data I've labeled the model with, and maybe on some additional parameters. And then one could say, okay, the expectation value of this observable is simply given by inserting it into the state sum, according to this formula. So that's some observable O that depends on the manifold and the labeling, and one evaluates it in that way. And that is something one can do in principle, and it makes sense, but the problem with this is if one does it in an unsystematic way, it usually gives something that is trivial in some way, simply zero or not interesting. So in order to get something interesting, one needs some additional data or parameters to define the observables. And it's not really clear which data one should use for that. So there are some partial results for the case of UQ of SU2, and also some ideas from physics, namely how to include particles into spin-fold models. But these ideas are not precise, and it's not clear if they make sense and in which context the second point makes sense. But it's not clear what is the general pattern, and also not what is the mathematical structures one should use. And finally, there's another point in relation to the Turaev-Viro model, and that is if one is able to define observables, one should in some way recover the Reshetikhin-Turaev-Witten invariants, or invariants of color-ribbon graphs, because they arise from a different way of quantizing the same theory. So in some way one should be able to get them back if the theory is supposed to make sense. But for the ones one has so far, it's not clear at all how one can get them back. Okay. And so that was the motivation, and what we try to do is to define observables from different categories. And that has some physical interpretation, or there's some physics intuition behind it, namely to see observables as something like defects in a state sum model. So one can see the generalized Turaev-Viro model as simply a collection of independent tetrahedra that are labeled with data, namely objects and morphisms of the spherical category. And then one constructs the model by gluing these tetrahedra together. And the gluing condition is then that the objects and the morphisms on faces that are shared between the tetrahedra and the edges that are shared should simply be the same. And in this way one can interpret the Turaev-Viro invariant. So then the idea could be that one can relax these gluing conditions. But in order to relax it, one needs to relax it in a controlled way, and the way this is supposed to be controlled is by the higher categories. Okay. And this one can see really as something like introducing defects into a crystal, so it has some physics picture behind it. Okay. But in order to make this precise and to see what precisely will happen with this relaxed gluing conditions, one needs to think about it. And so the basic idea is to interpret the spherical category as a two-category that has a single object. So the two-category has a single object. The one morphisms are the objects of the spherical category. The tensor product in the spherical category is the horizontal composition. And the two morphisms of the two category are the morphisms of the spherical category. The vertical composition is simply the composition of the morphisms. If one does this, one can consider an associated subcategory of the category of two categories. So the category of two categories has as objects two categories, as one morphisms functors between them, as two morphisms so-called pseudo-natural transformations, and as three morphisms modifications. And it's going to be a subcategory because one wants to restrict first to two categories that have just a single object. Also one wants to impose compatibility with the spherical category. So one will get a subcategory. And the idea is then that to say, okay, so if I glue two tetrahedra, now I'm not requiring that the objects and the morphism on the shared side match, but that they're related by a functor between from the spherical category to itself later. And if one wants to introduce such a defect, one is not finished here because now one needs to think about also what happens if one glues all the tetrahedra that share a common edge. So one starts with one. Then one uses a functor and glues it to another one uses another functor, and finally one closes the circle. When one sees here there's a certain contradiction. So here I have the object B, f of B, and here also hg of B. So somehow I need to resolve this contradiction, and to resolve it one has to assign a pseudo-natural transformation between the associated functors to each of the edges. But it's still not finished because one needs also to say what happens if one glues now several tetrahedra around a shared vertex. And in this case, so now I'm gluing simply one tetrahedron below the three ones I've already glued. And in the middle there's now a vertex which is surrounded by tetrahedra. In this case one then has four pseudo-natural transformations, and these four pseudo-natural transformations belong to the four edges that meet in the middle. And then one has to impose another consistency condition, namely that for each vertex one will associate a modification between the associated pseudo-natural transformations. Okay. So that is roughly the picture. So what we wanted to do, and now I'm going to make this precise by saying what precisely do we consider as a higher category, and what mathematical structure do these functors, pseudo-natural transformations, and modifications belong to. Okay. So because we need the compatibility with the data of the model, that is a non-degenerate semi-simple spherical category, what it will turn out that the functors and pseudo-natural transformations and modifications will form the gray category, and not just the gray category, but the gray category that has two duality operations. And in the following I'll call this sphere-cut for the category of spherical categories. Okay. So what is sphere-cut? It's obtained from the gray category 2-cut by restricting to two categories that have a single object. Then essentially one gets the category of monoidal categories. And then in addition to that, to impose some additional compatibility conditions for the structure of the spherical category. And then one gets sphere-cut. Okay. So then the objects of this category are supposed to be spherical categories, interpreted as two categories with a single object. And the one morphisms are supposed to be spherical functors. So what do I mean by spherical functors? That are supposed to be strict tensor functors between the spherical categories. So it means they're compatible with the tensor product and also with the unit. And they're supposed to satisfy an additional condition that makes them compatible with the duality. So star was the duality operation in the spherical category, and the epsilon is the co-evaluation. Okay. And one can represent these functors graphically by regions in two-dimensional diagrams. So essentially I can see one of these functors as a plane. So here I have a plane. Then I have a morphism in the spherical category, and then I apply the functor to it by putting the plane on top of this morphism. Sorry. Like this. And in the diagrams, they will correspond to regions in the diagram. Okay, so this is the one morphisms. The two morphisms are supposed to be spherical transformations between spherical functors. So this means they are pseudo-natural transformations So in the special case where I have two categories, it has just a single object. Pseudo-natural transformation consists of an object in the spherical category together with a collection of isomorphisms that go from the tensor product. So collection means I get one for each object of the spherical category. And they go from the tensor product of an object with the functor applied to this object A to the opposite tensor product of the other functor. Okay, and they're not just any isomorphisms, but they are supposed to satisfy compatibility conditions. So they're supposed to be natural isomorphisms, compatible with the unit, and compatible with the tensor product. And in terms of pictures, one can depict these morphisms by a line between two different regions. So I have a white region, which is labeled with the functor F, and a gray region with the functor G. And in between I have this kind of dashed blue line that carries the special object of the spherical transformation. And here one sees simply an object in the spherical category. Here's f of a and here's g of a. So that's the way one can represent them. And then all the defining properties also have pictures. So the naturality means I can pull the vertices that stand for morphism in the spherical category, I can pull them to the other side. The compatibility with the unit simply means I still do not have to draw the unit object, that's simply the empty arrow. And the compatibility with the tensor product is this picture. Okay, but they're not just pseudo-natural transformations, but I have to satisfy another condition which I call the spherical condition. And because it looks complicated when I write it out, I just give the picture. It has something to do with the composition of various duals of the co-evaluation and so on. Okay. And the three morphisms are then supposed to be modifications between spherical transformations. So in the case where one has a two category with only a single object, modification is a morphism between these special objects that are associated with the pseudo-natural transformations. So x nu and x mu are objects in the spherical category, and the modification is a morphism between them. And this is supposed to commute with all other morphisms. And in the picture, one can denote it by a vertex on these dashed lines. And the condition that it commutes simply means that I can move these type of vertices along the dashed lines like that. Okay. So this is the objects 1, 2, and 3 morphisms. So then one also has product operations. So one has the gray product that is simply the composition of spherical functors. So the categories, of course, need to match, and then I can compose them. Then one has a composition of spherical functors with spherical transformations and modifications. In fact, one has two, one from the left and one from the right. So from the left means one simply applies this functor to the associated morphisms. And from the right means one doesn't do anything to the morphisms, but one simply applies it here in this condition like that. And then there's a horizontal composition of spherical transformations and modifications. Again, the functors that are the sources and the targets, they must match. And the picture for this is simply drawing them next to each other. So this is like a higher category counterpart of the tensor product. Okay, I'm sorry. Yes, and this is again defined in terms of this collection of morphisms. And finally, yes, and they're similar for the modification. And finally, one has a vertical composition of modifications, that is simply the composition of the associated morphisms. And the picture looks like this. Okay, so these are the product operations. So finally, one has two more bits of information, or one more bit of information for the gray category, and that is the thing that some people call tensorator. So that means that for all spherical, so one has a pair of two spherical transformations, there's no matching conditions, it can be just any. One has an invertible modification that goes from the tensor product of them, composed with certain functors, to the tensor product in the opposite direction. And the picture for this looks somewhat like the braiding, like the braiding in a ribbon category, for example. Only that now all the regions are labeled with different functors, and one has to keep track of the functors that everything matches. And this tensorator commutes with the modifications. That means in the diagram I can slide vertices for modifications along these lines, also along the other line. I haven't given a picture. And also it satisfies something that looks like a diagram for a Young-Baxter equation, only now everything is labeled with functors and becomes more complicated. Okay, so that is roughly the gray category structure that one gets from this category sphere cut, but that is not all, because the plan was to label oriented edges and oriented faces in the triangulation data from the category, because the edges and the faces are oriented. I need to have some notion of what I'm going to do if I invert the orientation. And for this one needs the duality operations. So there one needs two. One, so this is for reversing the orientation, and one needs one that reverses for reversing the orientation of an edge, and the other one for reversing the orientation of a face. And the first one, which I denote also by a star, is a strict functor of gray categories that comes from the duality in the spherical category. So it acts trivial on the spherical functors, and it acts on the spherical transformation by simply taking this collection of morphisms to the double dual here. And the action on modifications is simply taking the dual of the morphism. And one can show that this is a strict functor of gray categories. It's also an involution, so it satisfies star is equal to 1. And it's contravariant with respect to the horizontal and vertical composition. And one does not just get a duality, but one gets something else. Namely, the spherical condition is equivalent to stating that the morphisms associated with the special objects of the spherical transformations define a modification from the identity spherical transformation to the tensor product. And the picture for this is simply an oriented arc, now with a dashed line, that has functors to the left and the right. And one can show then again it satisfies exactly the same analogous identities to the identities for the spherical category. So this diagram is well defined. This is equal here, composing this generalized co-evaluation, and the evaluation gives the identity, and one can slide modifications past it. It gets the goal. Okay, so that is the first type of duality that corresponds to inverting the orientation of edges. Then there's a second type of duality one needs, and for this we need to restrict to non-degenerate spherical categories and spherical functors that are invertible. So the invertible sounds bad at first because it seems such a strong requirement, but it's not that strong, because just being a spherical functor means already that on each of the morphism spaces there are bijections. So saying it's invertible means simply saying that they do not do anything terrible with the object, so they're bijective and the objects too. And it's also not clear at that stage. Maybe one can relax this condition, but then one gets a lot of complicated technical complications. So for the moment I suppose simply that the categories are non-degenerate and the functors are invertible. And then this condition, by the way, has a good interpretation in terms of the spherical categories, because it means that the pairing of the morphisms in the spherical category is preserved. Okay. So using this one, we find a weak functor of gray categories. That action of this functor on the spherical functor is given by taking the inverse. And the action of spherical transformations is given by composing them from the left and from the right with the inverse of the starting functor and the target functor, like this. And for the modifications it's similar. And this is only a weak functor of gray categories, and it's contravariant with respect to the gray product, that is the composition of functors, and also with respect to the horizontal composition. And one can ask, what does it correspond to in terms of diagrams? So locally it corresponds to looking at a plane from the other side, but only locally, so it has something to do with folds in diagrams and also cusps in diagrams if one tries to make some projection of planes. And the invertibility of the functors is important because it says that these folds and these cusps are essentially trivial or largely trivial. And finally, these two duality operations are not independent, but there's a certain compatibility between them. And that's this identity here. Okay. So this is the data one needs to define the observables. So one has a gray category formed by spherical categories, functors between them, spherical transformations and modifications. And this is two duality operations that allows us to invert the orientations of edges and planes, edges and faces. Okay. So now the question is how to incorporate all this into the model. So essentially what we have now as data for the observable is that each oriented face or triangle we associate a spherical functor, and to the opposite face its dual. Of course this can also always be trivial, so the observables can be such that for many of the faces in the triangulation these functors are simply trivial. Then to each oriented edge plus a choice of one of the tetrahedra that meet there, we associate a spherical transformation from the product of these functors to the identity. So here one needs to choose a tetrahedron because here one has a sort of a circle of functors and one needs to split it up at a certain somewhere. And this somewhere is given by the choice of the tetrahedron. And finally, okay, and for the reversed orientation one takes the dual of the spherical transformation. And finally, for each vertex I need to make more choices. The first is one needs to choose a maximal tree. So that will then define a set of generators of the fundamental group of a punctured sphere and a punctured disk. The punctures corresponding to the incoming edges. And this gives a cyclic ordering of the incoming edges. And I also need to choose one of the tetrahedra that meet there. That makes a linear ordering out of the cyclic ordering. And then one associates to this vertex a modification between the associated spherical transformations. And here the numbers refer to the ordering induced by the tree. Okay, so this is the picture. Now one would like to incorporate it into the model in a similar way as it was done with the model without observables. So the model without observables, one had simplices, the edges and faces were labeled by something, and whenever one glues two simplices together, the things have to match. Now we have introduced gaps in the model, so we cannot simply work with the simplices anymore, but if we want something similar, where one glues together certain pieces that match, one needs to have something more complicated. So one needs to in some way refine the triangulation, and for this we look at the second derived complex. That means we do two barycentric subdivisions. So barycentric subdivision means I add another vertex in the middle of each face, of each tetrahedron and of each edge. And then I connect them like I've shown here. And if one does this twice, one gets the second derived complex of the triangulation. So here I've shown for a tetrahedron. And the good thing about it is it sort of decomposes this into polyhedra that are neighbors either to a vertex, that one would be a neighbor to a vertex, to an edge, that would be the dark gray ones. The black ones are neighbor of a face, and the one in the middle, the white one, is a neighbor of a tetrahedron. And if one does this for every tetrahedron in the triangulation and then smoothes out the resulting pieces, one gets a sort of decomposition of the piecewise linear manifold into certain polyhedra. So the polyhedra are quite complicated, so I've shown them here. The labeling, the letters I've put here tell you how they glue together. So if I have a side here that is labeled F, it means it's glued to a face. And similar for the sides with E and V. Okay, yes, and so the gluing is like this. So they're quite complicated, but they allow one to really fit the data for the observables and the data for the spherical category together on this polyhedra and then to evaluate it in a simple way. So that's the point of introducing them. Okay, so now we can take these polyhedra and label them with data. So there are now two bits of data. So the first is the intrinsic data that comes from the spherical category, and that would define the model without the observables. The second data is the data for defining the observables. So that comes from this gray category sphere cut, and it defines the observables. So then one takes all the polyhedra and one starts labeling them. So one starts with the face polyhedron. So there one takes one of the hexagonal faces and three of the edges that come up there and labels them with simple objects, as I've shown here. The other three edges of this hexagonal face one labels with spherical transformation from the identity to the identity, and that should be associated with simple objects also. And then the face itself one labels with the morphism in the spherical category. The quadrilateral faces one labels with the spherical functor, and then the hexagon on the other sides gets simply the labels are the images of the data on the other side under this functor. Okay, and the labeling of the face polyhedron then induces some labels on the sides of the edge tetrahedron and vertex polyhedra also, wherever they're glued to it. So here one sees these sides are glued to the sides of the face polyhedron, so they're labeled with functors and with object in the spherical category. Similar, the tetrahedron polyhedron has a face that is labeled with morphism, and the vertex polyhedron also gets labeled with functors. Then one looks at the edge polyhedron, and it's labeled already by a lot of functors, and now one picks one of the not labeled faces, or not so far labeled faces, and labels it with a spherical transformation from the product of all these functors to the identity. And this again then induces some labelings of the tetrahedron or of the vertex polyhedron. Finally, the tetrahedron one has several sides which are not labeled yet, exactly 4, and these are labeled then with modifications between the incoming pseudo-natural transformations that border on this space. And finally, so this again shows up also on the vertex polyhedron, and finally one labels the vertex with a modification. So that's the pink modification, and one sees it doesn't go everywhere because this reflects the choice of the maximal tree. Okay. So the advantage of this is that now one can work with diagrams that are directly related to this labeling and that they can be in principle read off from it. So how does one do this? Each of the data that is assigned to a face and to an edge of these polyhedra gives some diagram for this gray category sphere cut and also for the spherical category. So here an example, so that's a face that comes from the face polyhedron that simply corresponds to a functor and a sphere cut, and here one has an object in the spherical category. First it's B, then it goes into the surface labeled by the functor and becomes f of B. Then one has these morphisms that are labeling the hexagonal faces. The picture is simply the one I've given here. So one has 3 objects of the spherical category and 3 objects from the higher category. And in principle, the pictures, the diagrams for this is always obtained by simply taking the dual of the picture. So each face is replaced by a vertex, and each edge is replaced by dual edge. And one can do this similar for the faces that label a pseudo-natural transformation, for the modifications, and finally for the big modification that was located at the vertex polyhedron. So this is like a dictionary for translating everything into category diagrams. And if I now look at the tetrahedron, I can compose all the data that lives there along the shared edges, and one gets a closed string diagram. So this diagram involves data from the spherical category, so that's the black data, and it involves data from sphere cut, so that's the blue and dashed data. And it looks complicated, but it gives a diagram that one can evaluate. So it associates, it's a closed diagram, so it associates to this labeled tetrahedron a complex number. And using this one can now construct the state sum or the invariant in a similar way as I did before. So one takes the product over all labeled oriented tetrahedra and the associated numbers, one multiplies this with the Q dimension of the objects associated to the edges. So this is preserved by the functors, so there can be no problems from the functors. Then one sums over all labelings, but now the sum is taken only over the intrinsic data, not over the observable data. And one multiplies it with the scale factor. So in principle now, this sum one can evaluate it, and the easiest way to do this is by using diagrams. Okay. So one takes the sum over the labelings with the intrinsic data and then uses the identities, essentially all the diagrams I've given before for the spherical category and for the gray category sphere cut. And if one evaluates it in that way, one finds that if one has a free ball with a boundary, the resulting state sum is given by the intrinsic data on the boundary and by the observable data in the interior on the boundary. And one can evaluate it then further by projecting this observable data in the interior on the boundary. And that gives then a diagram, this is a string diagram for the gray category sphere cut and for the spherical category. So generically looks like this, so there's some functors in it and spherical transformation, but also data from the spherical category. And one can then also evaluate the case of a closed manifold. So if one has a closed manifold, for instance S3, then the state sum will be given by the observable data in the interior, because there is no boundary. And one can again evaluate it by projecting the data in the interior on a plane. And that then gives a string diagram for the spherical category. So it looks a lot simpler because there's no boundary data. And one can show that this is an invariant of a graph in a piecewise linear three-manifold, and it's invariant under Pachner moves that do not affect the observables, so the observable data. So if I can apply Pachner moves to all the tetrahedra that do not contain observable data. Okay. Okay, so this is kind of a rough picture of how this works. So the principle is always to just translate everything into the diagrams and then use the diagrams that define the spherical category and the category sphere cut to evaluate it. So now I'll come to the last part of the talk, namely the relation to the Turaev-Viro invariants. So why does one expect such a relation? One expects such a relation because the 3D, essentially because 3D gravity with positive cosmological constant and Euclidean signature is related to Chern-Simons theory. And one can consider Chern-Simons theory as a gauge group that is simply two copies of one and the same group. For example, in Euclidean 3D gravity with positive cosmological constant. And then there are exactly two ways of quantizing, well, there are two main ways of quantizing it. One is to construct the associated Turaev-Viro invariant, but this Turaev-Viro invariant will be then based on the representation theory of a Q-deformed universal enveloping algebra of the Lie algebra of H at the root of unity. The other way of quantizing the theory is the so-called Reshetikhin-Turaev-Witten invariant or Reshetikhin-Turaev invariants. And these are constructed from the representation theory of the Grinfeld double of this Q-deformed universal enveloping algebra. And that this is also up to a twist if it's simply topology of this. Okay. And so one knows what is the relation between on the level of state sum without any observables, namely that the state sum for the Turaev-Viro invariant is something like the absolute value squared of the Reshetikhin-Turaev-Witten invariant. But the question is now, what about the observables? So one knows how to construct observables in the Reshetikhin-Turaev-Witten approach. The observables should be simply not invariants for the Grinfeld or link invariants for the Grinfeld double, for representations of the Grinfeld double of this Q-deformed universal enveloping algebra. And for the Turaev-Viro approach, we have constructed observables. On the closed manifold, there are string diagrams for the gray category sphere cut, some subcategory thereof that is associated with this Q-deformed universal enveloping algebra. But, okay, so if these are two different but equivalent quantization of the theory, then they should agree also on the level of observables. Otherwise, one cannot see them as equivalent. So a priori, it's not clear how this is equivalent and how it's related. And how the observables introduced now, are they related to the Reshetikhin-Turaev invariants or not invariants? And to understand the relation between the two types of invariants, one needs to think about the representation categories, namely the relation between category of a Hopf algebra and its Drinfeld double. That's because here one has a Hopf algebra and here one on the other side one considers its Drinfeld double. Okay, so the relation between the two is given by the so-called center construction. So one has a Hopf algebra and the finite dimensional representation form a monoidal category. The two words. On the other hand, one can do the Drinfeld double construction and one gets the Drinfeld double of the Hopf algebra, which is a quasi-triangular Hopf algebra. And the finite dimensional representations of this form a braided monoidal category in pools. And now one can also do the same step on the category side, and there it corresponds to the center construction. So the center of this monoidal category C is then a braided monoidal category. Okay. So somehow, if the relation is there, it must be given by the center construction, and one needs to see how this is related with the observables. Okay, and the idea to see this is to consider the observables introduced before in the model where one says all the functors are trivial. So they're just identity functors, but the modifications and spherical transformations are not supposed to be trivial. And one can show that in the case where all the functors are trivial, this gray category sphere cut reduces to the center of the spherical category C. So the spherical transformations are objects in the center, and the modifications are the morphisms in the center. And one can see this also in terms of diagrams or visualize it. So before one described pseudo-natural transformations with the functor f on one side and the functor g on the other side, and now these functors have simply disappeared, their identity. Here one has the co-evaluation, and here one has a modification that is now simply a morphism in the center of C. But now one has a new, so all of these diagrams, the three diagram components before are similar to the ones that are present in the spherical category. But in the gray category, one also had the tensorator. And this tensorator now reduces to the braiding. And that's a new diagram that was not present in the spherical category. And that makes sense because the center construction is supposed to give a braided category. So this is how one gets the braiding of the braided category. Then one has composition. Here one has the horizontal composition of pseudo-natural transformations becomes simply the tensor product in the monoidal category. And the composition of modifications becomes the composition of morphisms. And one has also identities. So this is simply these are the identities that is also present in the spherical category. It is sliding morphism past the co-evaluation. Then one has the compatibility with the tensor product. And one has the co-evaluation with the evaluation gives the identity, and one has left trace is equal to right trace. But now one also has a new identity that looks like the Young-Baxter equation. And that is one would expect in a braided monoidal category. One can then see that the observables, if one considers the model with trivial functors on a closed manifold such as S3, it gives first a gray category diagram, it gives a category diagram for the gray category sphere cut. But when the functors are trivial, this gives a closed string diagram for the center of the spherical category. And if all modifications in these diagrams are braidings, one gets a link and a not invariant for the center of the spherical category. So that means one can obtain the Turaev-Invariants for the center of the spherical category as a special case from the observables of the Turaev-Viro model, where observables were constructed for the spherical categories. Okay, so now I'll come to the outlook and conclusions. So the point of the work was to define something that physicists call observables for the generalized Turaev-Viro models that are formulated in terms of spherical categories. So the idea was simply to relax the gluing conditions for tetrahedra, sort of introducing gaps into the model. So when two tetrahedra meet, now the objects and morphisms on the edges and faces do not have to be identical but only related by functors. And then one obtained some consistency condition, and that led to a decoration of the model with data from a gray category sphere cut. So each face is decorated with a spherical functor, each edge with a spherical transformation, and the vertices with modifications. And from this data, one obtains invariants of graphs that are embedded in piecewise linear manifolds, and this provides some consistent and also general notion of observable for the three-dimensional state-sum models of Turaev-Viro type, because it provides some sort of mathematical framework where one can say now what is an observable, and which is not limited to some very specific case, but is a general definition. And also this observables, from these observables, as one would expect, if one believes that the Reshetikhin-Turaev approach and the Turaev-Viro approach are equivalent, one can recover the Reshetikhin-Turaev invariants. Okay. Then there are many open questions. I mean, there are some detailed questions. For example, in various conditions such as the invertibility of the functors can be relaxed. And also one would like to construct some concrete examples and investigate this for concrete cases. For example, for UQ of the representation category of UQ of SU2 or for finite groups. And also one thing I'm interested in is really to see, can one give a clear interpretation to this in the context of gravity. So the defects that correspond to the spherical transformations should in some way be related to incorporating point particles into these models, or interaction between gravity and particles. But it's completely unclear what, for instance, these functors would mean, or the defects associated with the functors. So that's some things I want to look at later. Okay.
Other questions?
So what sort of data does this give rise to on the level of the Hilbert spaces that you assign to two-dimensional?
You mean the observables or the... Okay, so first these Hilbert spaces are simply finite dimensional vector spaces. And then the picture is that if you have a boundary, the observables can come up on the boundary. And then it will be one dimension lower. So normally the functor would correspond to a region, and there on the boundary corresponds to a line. And the spherical transformation would correspond to a point.
Topologically, what sort of features are these observables picking up on now?
When you say what features are they picking up, you mean picking up from what?
Well, what features are they observing as observables?
Ah, okay. You mean like the physical interpretation of that? So essentially, I think they're observing defects. So if what I understand is kind of correct, but that's not something I know, that's something that is an intuition. If you want to incorporate a point particle into a model like this, you would have two parameters associated to it, the mass and the, something that is like an internal angular momentum. If this point particle then comes up to the boundary, you have a point there that is labeled by two parameters that characterize this this spherical transformation. And the two parameters would then be the mass of the particle and also the angular momentum. And if one has more particles, it will pick up more. It will pick up the relative motion. For example, I could have something like a sphere. But all of this is speculative. So it should be like that, but I haven't proved it. So one has so this is B3, and then one has the boundary here, and then one has some dots. These would be particles. And then one has some lines that go into the interior. Maybe here's another one. So here, for example, one would have particles that somehow braid in the interior. So this would tell you something about how the particles interacted. So, for example, you could also consider something like a cylinder, where you have some particle here, and another particle here, and here at the bottom also. And now they, inside of the cylinder, they wind around each other like this. So this would tell you that the particles have interacted. So at the first state you consider as two particles, the second two, but in between something happened. And that would be interpreted as a sort of topological interaction of the particles. But as I said, this is only for the case where the functors are trivial, and for the functors one simply has no clue. I mean, that would be something really interesting to see what this is in terms of physics. And for the, yes, so here you could also consider, depending on what you consider, like what spherical category you consider, you will have different numbers of particles that label the properties of the, different numbers of parameters that label the property of this generalized particles. But essentially particles, so the kind of intrinsic properties of the particles are what characterizes the representation, and then the interaction between them is given by essentially topology in the interior, how the world lines, or how these lines wind around each other. But there's a lot of work to be done to make this precise.
In similar models of loop quantum gravity, one has a problem that the observables have a gauge invariance, and people there are not able to install this Hamiltonian constraint to actually get observable. So I'm not really sure I understand how you get the dynamics on your model at the moment, but are your observables somehow susceptible to a gauging?
Yes, so I mean the rough answer is, so the picture in 3 dimensions is much more simple, and that's why one can do it. So implementing the constraint in 3 dimensions is much easier than the higher dimensional constraint, because the constraint is essentially a flatness constraint on a gauge field classically. One still will have some residual gauge invariance, but a lot of this one has already taken away by working in tetrahedra and kind of discretizing the model. So essentially what the gauge invariance kind of boils down to is, for example, if I try to introduce an observable by simply saying, okay, I take my Turaev-Viro model, and what I'll do then is, for example, I'll label one edge. So here I simply don't sum over the labels, but I fix a label here rho, and here I fix a label tau. And I evaluate this. Then gauge invariance would manifest itself in the fact that this will give you, so if tau and rho are simple, the gauge invariance would tell you that essentially this is 0, like the state sum will become 0 unless rho is equal to tau. So essentially, so what the gauge invariance does, it makes things disappear unless they give you something closed. If you have no boundary, things that are not closed will disappear. So if you have, for example, something that looks like this, like a closed circle where everything is labeled by rho, this will give you something non-trivial, namely simply the knot polynomial for the circle, also for a general knot. But if you have something that is just like a line in the interior, or if you have, like I showed here, some things that are different and that meet, like different simple objects that meet, then you get something trivial. But this is really only because the theory in 3 dimensions it's much simpler, it's topological, and in 4 dimensions, no.